us hints onto the initial diatomic molecules and other ones were computational studies. So these are simulations. We use computation.
Yeah, good morning. I just came from the keynote lecture I gave this morning. It's about the study of the formation of organic molecules. Not any organic molecules, but those that probably will lead to the synthesis of amino acids in space. They were detected in several clouds, in particular in Sagittarius B2. Some of these molecules can form in the gas phase, but others cannot because of the extreme physical conditions that are governed in those clouds. For example, very low temperatures, around 10 Kelvin, and very low pressures. So the possibility of a third body, which is the dust grain, that will play the role sometimes of a catalyst and sometimes of a third body to dissipate that excess energy, so the formed molecule does not dissociate and get back to the gas phase. A few examples have been mentioned in my presentation. They include the formation of propyl cyanide that has a particular form in its isoconformer, which is a branched form that is linked to the shape of amino acids, which lead to the formation of prebiotics in space, and might shed the light on how these molecules formed before arriving to the early Earth. So the study is based on computational chemistry. We use sophisticated tools to treat the electronic interactions between the different radicals to lead to the formation of isopropyl cyanide and its linear form, normal propyl cyanide, that has also been detected in Sagittarius B2 in the 2009 and 2014 respectively. So we have provided reaction paths for radical-radical association, and these are barrierless, so the occurrence of these reactions is very favorable in the very low temperatures of the interstellar medium, and they confirm the feasibility and the formation of these molecules in such harsh conditions. The other example of molecules I have presented is the simplest aldehyde, which is acetaldehyde. It has been detected since the 1970s and is very important in the synthesis of biochemical molecules. It can lead to glycolaldehyde, acrolein, so several chain chemistry there, very interesting in the understanding of the origins of life. And we have adopted another model of ice grain, which is pure water ice, cubic water ice, doped with methanol, and was attacked by carbon atom in its electron ground state, which is very abundant in the interstellar medium, in particular in Sagittarius B2, where acetaldehyde was detected, and not only there, but in many other regions of space. And we provide, in this particular case, because of the small size of the ice cluster, ab initio calculations based on coupled clusters. So we have been able to predict quantitative data about the reaction paths that involve really several complexes, which might involve different spin states, the singlet spin state and also the triplet spin state. And we have been able to show how we can get this spin flip to provide the formation of acetaldehyde in its singlet spin state, where it has been detected. And we have computed rate constants versus temperature, for which we can give analytical functions that are very useful for our astronomer colleagues to be used in their models and to lead to details about abundances in the region where the molecules have been detected. The third example that I have also mentioned in my presentation is dealing with the formation of formamide and acetamide. These molecules are of greatest interest in the interpretation of the chain reactions that lead to amino acids and complex organic molecules leading to the origin of life because of this peptide bond that is crucial in linking polymers of amino acids, and the understanding how, when, and where these peptide bonds occurred before arriving on the first periods of the young Earth is so important for us as chemists. So we have performed calculations of the pathways starting from HCN molecules adsorbed on a model of pure water ice, and we show in this particular case how the grain ice can play the role of a catalysis because it is involved in the reactivity, and we can see that the addition of protons on this ice model, so having hydronium on top of it, can catalyze the reaction and reduce the reaction barriers by more than 50 kilocalories per mole, therefore providing the detected formamide and acetamide, and we can show through these quantum computational studies how the reactions are concerted and divided in two steps. The first one being proton transfer to the HCN, and then water molecule covalent bond to the oxygen and carbon, so that we obtain in the end the desired molecules with thermal energetics that are really convenient for the detection of these molecules in the regions where they were observed. And I would like you to go into the details of my presentation, so it will give you more details about the methodologies that have been used, and I hope that you find this topic very interesting to you and to the students that would like to follow up these kind of calculations in the future.